Hi, my name is Fabian Majcen from the University of Vienna, and today I want to tell you about my master's thesis about experimental inverse design Magnonics. Nowadays, computing is everywhere, and it's very energy hungry. Faster processors demand more power, and we're starting to hit the limit when downscaling components. So to keep up, we need to rethink how we compute. One promising direction is Magnonics, where we use spin waves instead of electric charges to carry the information. Spin waves are collective oscillations of magnetic moments. Since they don't actually move charge, they are able to avoid resistive losses. They operate from gigahertz to terahertz frequencies, making them ideal for RF applications like 5G and beyond. Additionally, they offer high potential for downscaling. Recently, the use of inverse design in Magnonics has sparked a wave of new innovative research. In my thesis, I contributed to building the first ever reconfigurable inverse design Magnonic device. The experiment is based on propagating spin wave spectroscopy. Here, a vector network analyzer creates a microwave signal. This excites spin waves via microstrip antennas in our yttrium iron garnet ferromagnetic film. This is our input. On the other side, output antennas detect the spin waves again, and the vector network analyzer shows us a transmission spectrum. This electromagnet supplies an external magnetic field, which saturates our sample and defines spin wave propagation dynamics. Now comes the twist. While they propagate, we're able to influence them, and we're doing this by these 49 omega-shaped current loops. Each of them is individually controllable by one of these current sources. As a current flows through one of these loops, they create an additional localized magnetic field. By then finding the right configuration of currents, we can create the desired functionality. This is what inverse design is all about. We don't create a structure for every functionality. We rather use a reconfigurable platform and just have to find the right settings. All the devices of the experiment are remotely controlled. And then an optimization algorithm, like a direct search or genetic algorithm, is used to find the right current configuration. The device essentially optimizes itself. It sets a current configuration, measures the transmission characteristic, and then repeats this process until the target behavior is achieved. Using this approach, we created several RF functionalities, like notch filters, where a specific frequency band is filtered out of the signal. We were able to create this over a broad spectrum and with different bandwidths. Additionally, we created a frequency demultiplexer, where different frequencies are sent to the same input, but then they are filtered to different outputs. Over the course of 2 years, I contributed to this project by helping build the experimental setup, developing drivers for all the devices, and testing and tailoring optimization algorithms for this specific purpose. I carried out experiments, analyzed data, and did some simulations. All the effort paid off. The device works, and the results gathered during my master studies were even published in Nature Electronics. Additional work I contributed to, where we created Magnonic logic gates on this same platform, were published just today in Science Advances. This new class of Magnonic device demonstrates a wave-based, reconfigurable computing architecture, and it's very interesting for unconventional computing applications, like neuromorphic computing, which I'm now exploring during my PhD. Additionally, emerging AI technologies are very interesting for advanced optimization processes. Thank you for watching, and thanks to my group for all the support during my research.
Don't